Hello friends, today we will be performing an experiment of PN junction. The aim of the experiment is to determine the reverse saturation current of a given diode and to find out the material constant eta. We also will be finding the energy band gap. A PN junction plays an important role in semiconductor industry. This is the building block of most of the semiconductor devices like transistors, solar cells and integrated circuits. Here we have shown a PN junction in thermal equilibrium with zero bias voltage. A PN junction is generated when one side of a pure semiconductor is doped with acceptor impurity, making P region, and the other side is doped with donor impurity, making it N region. So on P side, the majority carriers are holes, whereas on N side, holes are in minority. On N side, majority carriers are electrons and they are in minority on the P side region. When junction is formed, the holes present in P region diffuse into the N region, leaving behind a negative charge in the P region. Similarly, electrons present in the N region diffuse into the P region, leaving behind the positive charge on the N side. As a junction is formed, each region becomes depleted from majority charge carriers around the junction. This region is known as depletion or space charge region, which generates an electric field that acts as a shield between the electron hole diffusion. The junction then behaves as a barrier which prevents further diffusion. The point is known as potential barrier. External voltage more than this potential barrier is required to put the junction in the operating condition. How voltage is connected across a PN junction is known as biasing. It is done in two ways, forward biasing and reverse biasing. When positive terminal of the battery is connected to the P region and negative to the N region, it is under forward bias condition. In that condition, it conducts to the maximum and offers low resistance. Whereas if we connect positive terminal to the N region and negative terminal to the P region, it is under reverse bias condition, and in that case it shows almost no current and shows the maximum resistance. So this is the characteristic curve of a junction diode. We can see that in forward biasing it conducts, whereas in reverse biasing very small current in terms of microamperes is flowing. So here it offers maximum resistance. So for an ideal diode, this resistance is in fact infinite. We can check it here in this diagram that we have shown a reverse bias condition here. So when we increase the reverse voltage, even then the current is almost constant. That's why it is known as reverse saturation current. In a PN junction diode, the reverse saturation current is due to the diffusive flow of minority electrons from P side to N side and the minority holes from N side to the P side. The reverse saturation current depends on the diffusion coefficient of electrons and holes. Because the minority carriers are thermally generated, so reverse saturation current is highly sensitive to the temperature change. And it is almost unaffected by the reverse voltage. The magnitude of reverse saturation current I naught is too small to be measured conveniently. The direct measurement of this current is therefore difficult, as it may cause errors also. So an alternative method is adopted. The current in PN junction is given by this equation. This reverse saturation current I naught here will be measured indirectly. So what is done is we take the graph, we assume that the exponential part is very large as compared to 1. So we drop 1 here and take the log of the equation. So that gives log I is equal to log I naught plus QV upon eta KT. So as if we draw a graph, ln I versus V. So it should be a straight line. And this line, mm, here log I naught will be the intercept of the line, whereas q upon eta kt should be the slope of the line. So by calculating the slope, we can find out the uh, material constant, and by finding this intercept of the line, we can calculate the reverse saturation current. So this is our experimental setup. This is a PN junction diode setup here, and this is our on off switch. These are the two knobs for varying the current and the temperature. This is a socket for the oven, and a diode is connected to this and kept inside the oven. This is the on off switch for the oven. Now this is the knob for changing the temperature. So this is the display unit for the temperature as well as current. So we can flick the knobs to the either to the current or the temperature, and accordingly reading will be taken. Now for example, this is at the current at present. We can change the current using this knob, and if we flick it to the temperature, so it is showing the room temperature to us. We can change with the help of this knob, we can change the switch on the oven and then change the temperature. So now these are the two connections, and which we connect the diode, and this is the knob for the current, and accordingly the bias and junction voltage will change. We take the readings with the junction, and this bias can be changed with the help of this knob. We have another option for connecting the CRO to see the all these waveforms. So here we connect the diode, and this is the socket for the connecting the CRO, and we switch on this. So this is the complete setup for the PN junction diode. Now let us perform the experiment for finding out the reverse saturation current and eta. For this, first of all, we flick the current temperature switch to current side, and then change the current in small steps. So initially say we give forward current of 100 microamperes to it, and note down the junction voltage. We can further increase the current and then note down the junction voltage, say for 200 microamperes. This process continues. We keep on taking the readings for changing the forward bias current and noting down the junction voltage, say up to 10,000 microamperes or 10 milliamperes. We note down the readings and observe that as we go on increasing the forward current, the junction voltage keeps on increasing. So we take the readings up to 10,000 microamperes or 10 milliamperes. Then this is the table for determination of reverse current and material constant. So corresponding to given forward current, we note down the junction voltage. On the right side of it, I have shown the clip of the readings we have taken in this experiment. So with the help of this set of readings, we plot a graph which comes out to be a straight line cutting the y-axis at ln I naught. So ln I naught we can read from this intercept, and with this value we can calculate the I naught, the reverse saturation current. Whereas if we look for the slope of this line, that gives the eta part of it, that is eta is equal to q upon kt into slope of the line. So from here we can find out the material constant. Now let us go for the second part of the experiment, that is to determine the energy band gap. Now let's discuss the theory in brief. So the diode forward current is given by this equation, where I naught is the reverse saturation current, which is given by this relation. So this relation contains the term of energy band gap here. So if we substitute the value of I naught in the second equation and dropping 1, we get a simpler relation, which for a constant current I and differentiating with respect to temperature T, we get VGO is equal to V minus T dV by dt minus M eta kT upon Q. At 300 Kelvin for silicon, this M eta kT upon Q is 0.078. Substituting this value and finding out the slope of the VT curve, we can calculate VGO. So for this purpose, a PN junction is kept under the test in a small fast temperature controller one. The temperature is adjusted from the room temperature to about 80 degrees centigrade, and from the readings of temperature and junction voltage we can find out the energy band gap. So this is the system, again the same system. Let's switch on it and then perform the next part of the experiment. So for this, first we will keep this temperature and current knob to the current range and adjust the current to 1 milliamperes, and then flick it to the temperature side. So at this moment it is showing the room temperature, which is 298 K. Now we will rotate this temperature knob to some value and switch on the oven. So we will see that this bulb glows. So it means that oven is heating up. We can see that the reading of the temperature is increasing. So when it flickers and then goes off, that time this temperature is stabilized. We note down this temperature and the corresponding junction voltage. Again we rotate the knob in clockwise direction so that again the bulb glows, that flickers, goes down, it means it stabilizes. Note down the temperature and the corresponding voltage. Again we will do the same procedure. Oven is on, it is heating it up. Not stabilized yet. This, now that it is thermal equilibrium, so the temperature is 312 and the corresponding junction voltage is 0.683 volts. So this process goes on and we take the reading for about 60 degrees centigrade. Difference. After that we note down all these readings and observe from the table. We observe that as we go on increasing the temperature, the junction voltage goes on decreasing. So this is the observation table. We have kept the current as 1 milliamperes and our room temperature is 298 kelvins, and this current is kept constant for one entire set. So on right hand side we have shown the readings we have taken in this experiment and then plotted the graph. So this graph is again a straight line having a negative slope, and then from here we calculate the slope and put the in the equation for VGO as we have already discussed. So in this part, for silicon at 300 Kelvin we substitute this value and then we can calculate the VGO. All these values which have been shown here, they are just for the reference and for an idea. You should take your own readings. So after calculating all these things, we can report the result for reverse saturation current. It will be somewhere in the nanoampere range. Then the material constant comes out to be 1.54 for the silicon, and the energy band gap is 1.18 electron volt. All these are for an idea. It is very important to discuss the precautions we have to follow. Before switching on the mains, we should ensure that all the knobs are at the minimum position. Then all the connections, for example, for the diode, should be neat and clean. The current should be increased in small steps. We should not increase it abruptly. Then when we switch on the oven, we should allow at least 3 to 4 minutes for to oven to stabilize. And because all our calculations are based on plotting the graph, so this graph should be plotted with perfection, because in both the parts we calculate the slope. So this is all about the experiment. Thanks for watching. Have a nice day.